All right, everybody, here's the solutions for the quiz from Wednesday, June 10th. My damn camera is not autofocusing. Come on. There we go. Okay, so let's go through them. Number one, we have a horizontal force of 25 newtons pulling a box along the table. Call that F applied is 25.0 newtons. And we want to find how much work it does in joules if it pulls the box 80 centimeters. Or 0.800 meters. I don't know if I've said this explicitly, but if you're going to do math with units, you have to be very careful to make sure that your units match. So here, I'll show you what I mean by going through the problem. So here we can just use our definition of force, or I'm sorry, our definition of work. Work in the x direction, or work done by a force pulling in the x direction, is going to be the x component of the force times the distance it's applied over, F delta x. So we'd multiply these together. We have 25 newtons, and here's where I just want to mention, you can't multiply this by 80 centimeters. Newtons and centimeters aren't compatible units. You have to multiply by meters. I probably didn't say that explicitly in my lecture notes. I probably should have, but just so you know, your units have to be consistent. And usually that means making sure that masses are in kilograms, forces are in newtons, distances are in meters, time is in seconds, velocities are in meters per second, accelerations are in meters per second squared, energy or work is in joules, etc. So that's just a PSA I thought I'd throw out there. Okay, anyway, doing out this multiplication, we find that the force that pulling the box does 20 joules of work. Pretty straightforward. All right, number two, similar kind of problem. We have a 75 Newton force pulling some object. I don't know what the object is. I'll just draw a blob. Pulling an object across the ground, and this force, however, is at an angle to the horizontal. So let's see, F applied is 75 newtons. Maybe that look more like 75. I hope I succeeded. And my damn camera stopped focusing yet. There we go. Okay. At a 25-degree angle above the horizontal, or 28-degree, sorry. 28-degree angle above horizontal. Okay, so now remember, the only force that does work is the force in the direction of the displacement. In this case, we want to find how much work the force does in joules if it pulls the object through a horizontal displacement of 8 meters. So delta x equals 8 meters. So here we're going to refine our equation for work a little bit. We'll call this FD cosine theta, where d is just the horizontal distance. So we can call delta x d. Otherwise, it's pretty straightforward like the first one is. We have our force of 75 newtons. We have our distance of 8 meters. And now, to account for the fact that the force is being applied not all in the horizontal direction, we include that cosine factor of cosine of 28 degrees. And plugging all that together should give you a force, or I'm sorry, work done of 530 joules. For number two. All right, let's do number 3A. This is a tricky one. I got several emails about this one, partly because there was actually a typo in my solution. I've rectified that, and I think I emailed everybody about it yesterday. So let's see. The coefficient of kinetic friction between a 20 kilogram box and the floor is 0.4. So here's our 20 kilogram box. And we'll call mu sub k is 0.400. Okay. And a pulling force F is applied that makes the box move at a constant speed. So here's our applied force. And this force is applied at an angle of 37 degrees to the horizontal. and we want to find what is the horizontal component of this force. So ultimately, we want to find F applied x. Now, how do we do that? Well, let's construct Newton's second law in the x direction. I'll do that here. So in the x direction, we have F net x equals, let's see, we have our x component of the applied force, and we have a friction force acting against it. And it moves at constant speed, and that's the key that you might have missed. Because it moves at constant speed, we know that the net force in the x direction is 0. If it wasn't 0, it wouldn't be moving at constant speed. There'd be some acceleration, but we're pulling it with just enough force so that it moves at a constant speed, so it's constantly canceling exactly the friction force pulling it back. So let's substitute in some expressions for this. Let's see, we know F applied x is going to be F, we'll leave that as F applied x because that's what we want to find. And then we know that the friction force is going to be minus mu sub k F n. And that's equal to 0. So the x component of the applied force is mu sub k Fn. Straightforward, right? Well, not quite, because there's another wrinkle. Because this force is applied at an angle, remember there's a y component, so that's going to affect the normal force, which in turn will affect the friction force, which in turn will affect the force applied in the x direction. So let's take a step to the side and analyze the forces in the y direction. So F net y is equal to the y component of the applied force. Then we have our gravitational force of minus mg. I'll write it out just as symbols first. Fg, and then we have Fn. And again, because this box isn't being lifted up or dropped or falling through the ground, the net force in the y direction is also going to be 0. So let's see. F applied, we'll actually write this out as F app sine theta. Force of gravity is just negative mg. And then Fn, F sub n, normal force, we'll keep as F sub n. And we want to solve for F sub n. So F sub n is going to be mg minus F applied sine theta. So let's plug that in for Fn up here. So F applied x equals mu sub k times mg minus F applied sine theta. Well, we know we're actually going to write out F applied x explicitly now. So that's going to become F applied cosine theta equals mu sub k mg minus F applied sine theta. So actually what we need to do is we need to find F applied and then apply our cosine theta factor to that to get the x component. So if we find F applied, if we want to solve for F applied, we're going to have to do this. We have to move this factor, or this term of F app sine theta over, multiply by mu sub k, because that's there. So we get F applied cosine theta plus mu sub k F applied sine theta equals mu sub k mg. So there's an expression that we can get to solve for the applied force. So I'm going to move on to another page because I'm running out of room, and this is a complex problem. Okay. So new page. We've got this, the applied force times the cosine of theta plus mu sub k times the applied force times the sine of theta equals mu sub k mg. So let's solve for F applied first. F applied can be pulled out as a common factor here. So we have then cos theta plus mu sub k sine theta in parentheses equals mu sub k mg. And then we can divide through by this stuff in the parentheses to just isolate F applied. So F applied is equal to mu sub k mg over cos theta plus mu sub k sine theta. So let's actually plug numbers in to get a value for the applied force. So we've got our mu sub k of 0.4, we've got our mass of 20 kilograms, and we have g 9.81 meters per second squared. Then we have cos 37 plus 0.4 times sine 37. And that should get you a net force, or an applied force, applied force of 75.5 newtons. Some of you got 75.4 kept up a bit. And that was actually what I had as the original answer, which is incorrect because I asked for the x component. I probably should have just asked for the applied force, but I asked for the x component, so we'll get that. So the x component is just going to be the applied force times the cosine of 37 degrees. So we have that 75.5 newtons times the cosine of 37.0 degrees, and we find the actual x component of that force is 60.3 newtons. I think I might have 60.2 as the one on the quiz, but again, 60.3 is within the error margin that I set. And that probably comes from rounding the applied force and maybe, no, that definitely comes from rounding the applied force. All right, so that's how you do 3A. 3B is much more straightforward than that. All it needs you to do is realize the definition of work. Actually, I should do a new page. All right, 3B. 3B just needs you to use the definition of work. So work equals F applied times distance times cosine theta. Or we could just write this as F applied x times distance it's applied over. We know it's dry date meters. We have our x component of the applied force. So then the work done should be 60.3 newtons. Did I say newtons when I gave you 60.3 before? Yes. Okay. 60.3 newtons times the 8 meters that it's dragged. And that should work out to be 482 joules. So that's how you get through question 3 on the quiz from Wednesday. All right, question number 4. If my damn camera will autofocus. There we go. Okay. So number 4. We want to know how much work it takes to accelerate a 1,300 kilogram car from rest to a speed of 20 meters per second. Sorry. So VI equals 0 meters per second, and VF equals 20 meters per second. And apparently we're neglecting friction here. Well, not necessarily. We're just interested in that work. And we actually want to find the work the work we need to do in kilojoules. Okay. So let's work out how much work we need to do that. In order to do that, we actually need to use the work energy theorem. Where the work done, the net work done, is equal to the change in kinetic energy. And so what we really want to do is figure out what the kinetic energies are of a car at rest, which is pretty straightforward at 0, and the kinetic energy of the car at that final speed of 20 meters per second, and what the difference between them is. So we have 1/2 mvf squared minus 1/2 mvi squared. And let's plug in our numbers here. So we have 1/2, we have our mass of 1,300 kilograms. I'm actually going to pull out these common factors of 1/2 m just because I don't want to have to keep writing it. So this will become something like this. Vf is 20 meters per second. And Vi we already know is 0. So, doing out that arithmetic, we find that it takes 2.60 times 10 to the 5th joules, or 260 kilojoules of energy, or work, to accelerate the car from 0 meters per second to 20 meters per second. Or it takes a net work of that. All right, number 5. Similar thing. We have a 1,200 kilogram car. Going 30 meters per second. And it applies its brakes and slows to a stop. So Vf now is 0 meters per second. And the braking force that it applies is 6 kilonewtons, or 6,000 newtons. And I'm actually going to tack on a negative sign to that because it's opposing the motion of the car. So we want to figure out how far in meters does the car go before stopping. So again, this is actually a work energy theorem thing. First, we want to find out how much work the brakes need to do to stop it. So that's a matter of the work energy theorem. So the net work is equal to the change in kinetic energy. So the change in kinetic energy in this case is going to be 1/2 m. I'm going to take this out. So I'm going to pull this out as a common factor. Then we have Vi squared minus, Vf squared minus Vi squared. Sorry. Here we have, let's see, 1,200 kilograms is the mass. And then we have our Vf of 0 meters per second, because it's stopping. And we have our Vi of 30 meters per second. Okay, so doing that out, we find that in order to stop the car, the brakes need to do negative 540,000 joules of work. So that's how much work they need to do. And that's negative because what the brakes are really doing is removing kinetic energy from the car by dissipating it into the surrounding environment as noise and heat and deformation of the wheels and things like that. Anyway, now that we know how much work the brakes need to do, and we know the force of the brake, we can work out what the distance they have to act over to do that much work is. So again, using our definition of work, just force times distance. I'll leave out the angle factor because it's being applied in the same direction, or it's being applied in the horizontal, entirely in the horizontal direction. So then the work that needs to be done is this, is the negative 540,000 joules. We have a braking force of negative 6,000 newtons. So we can solve for D to get the distance is the work divided by the force. So we have negative 5.40 times 10 to the 5th joules as the work that needs to be done. And the braking force is negative 6,000, or 6 times 10 to the 3 newtons. And that should lead to a distance of 90 meters. So that's number 5. You have to first figure out how much work the brakes need to do, and then you need to work out how the distance in which they need to act at a given force to do that much work. All right, 6A. We have a 40-gram rock, so a pretty small rock. And let's write that in kilograms, because we need to write it in kilograms in order to be able to do reasonable calculations with it. That is actually 0.0400 kilograms. All right, so that rock falls a distance of 25 centimeters to the ground. Or 0.250 meters. And we want to find its kinetic energy in joules just before it hits the ground. Now, we could actually use our knowledge of this damn camera. Sorry. Come on. You're halfway there, you stupid thing. All right. We could use our knowledge of... Seriously? We could use our knowledge of kinematics to do this by calculating the distance of the acceleration due to gravity and the distance it falls and calculate VF and then things like that. Or we could just use the fact that in this system, we can use our concept of gravitational potential energy and realize that that gravitational potential energy is going to transform as the rock falls into kinetic energy. So let's work out what its change in potential energy is. So that's going to be mg delta y. So its delta y is going to be, well, we'll see in a second. Its mass is 0.0400 kilograms. The acceleration of gravity is 9.81 meters per second squared. Nothing fancy there. And then its change in position is actually going to be yf minus yi, which is, it ends up at ground level, which we'll take to be 0. And it starts at 25 centimeters up, or 0.250 meters up, a little less than a foot off the ground. So its change in potential energy is, as you might be able to see, going to be negative and its change in potential energy is negative 0.0981 joules. Okay, that's its change in potential energy. Now remember, in the absence of other external forces other than gravity, like neglecting air resistance or friction or anything like that, we know that all of that gravitational potential energy is going to be transformed into kinetic energy. Specifically, if we write down the work energy theorem for this system, for this particular problem, we know that delta K is going to be negative delta UG. So, assuming it starts from rest, VI equals 0, I want to find VF. So 1/2 m VF squared minus VI squared equals negative delta UG, which we found. All right, so now we want to solve for VF. And solving for VF means we have to do a little bit of algebra. Let's see, we pick up a factor of 2, so we get VF equals, first off, there's a square on VF, so we know this is going to be under a square root sign. Then we have negative 2 delta UG over m. And then we'll have a plus VI squared, but that's really immaterial because VI is 0. So VF is then negative 2 times negative 0.0981 joules divided by the mass, which is 0.404 kilograms. And we'll just ignore that. We'll throw in the number just for completion's sake. We know that VI is 0. So, when we do all that out, we should find that the rock is going 2.21 meters per second when it hits the ground. So this is actually an example of what we'll get to on Monday, which is called conservation of mechanical energy. In the absence of forces like friction and air resistance, all sources of potential energy in a motion will be converted into kinetic energy as that motion proceeds. Now, depending on what kind of potential energy there is, and there's actually two that we're going to talk about. It'll affect the kinetic energy of the system in different ways, but we'll cross that bridge when we get to it. For now, all you need to know is that all that gravitational potential energy gets converted into kinetic energy, so right before it hits the ground, it's going 2.21 meters per second. And I just realized that I did part 6b, which was actually finding how fast it was going. So, oops. All right, finally, number 7. This was a long quiz. I'm sorry, I did not mean to make it quite this long. All right, number 7. We have a 2 kilogram mass that has 400 joules of kinetic energy. So M equals 2 kilograms, and it has, we'll call that K sub F, because it's just before it hits the ground. K sub F is 400 joules. Note the period there to indicate 3 sig figs. Just before it hits the ground, and we want to ignore air resistance, and we want to find out its initial height. All right, so it hit the ground, so we know YF equals 0 meters. Hit the ground with a kinetic energy of 400 joules. So this is sort of the reverse of the problem of problem 6. We know how much kinetic energy it has, which means we can work out how much gravitational potential energy it had at its initial height, and we can work out what that initial height was based on that amount of gravitational potential energy. So remember, delta K equals negative delta UG. So negative delta UG is negative mg, we'll actually write this out explicitly, yf minus yi, and that's equal to delta k. So if we assume that it was dropped from rest, which is our usual assumption, then its initial kinetic energy was 0 joules. And so delta k is just, well, it's kf minus ki, but it's just 400. So let's solve for yf, or I'm sorry, yi. Actually, I'm going to write that in explicitly. Kf minus Ki equals negative mg yf minus yi. And let's put in the things that we know to be 0. So Ki is 0 since it was dropped from rest, and yf was 0 since its ending point was ground level at 0 meters. So then we have this. Kf equals mg yi, and then we can just solve for yi to get its initial height. So that'd be kf over mg. So that's, let's see, we have 400 joules divided by a 2 kilogram mass, 2.00 kilograms, times the acceleration of gravity, 9.81 meters per second squared. And that gives us an initial height of 20.4 meters. All right, so that's it for the quiz from June 10th. If you have any questions about any of these quizzes, or I missed something that you did correctly, but the program marked it wrong or something, let me know. I've also changed my policy for these past 2 quizzes, June 6th and June 8th, to be infinite tries. I guess it was definitely not a good idea to just limit you to 1 try and then split up the problems. That was kind of a boneheaded move on my part. I don't know why I needed somebody else to point that out to me, but it is what it is. You guys can still, I think, mess with quiz 8 or June 8th quiz and June 10th quiz, and from now on, the quizzes will either be all essay response or infinite tries if I do numerical responses. All right.